good morning to everyone. The title is quite different from the one that you have in the conference. We did some changing at the last minute and it was not updated. But the content is more or less the same. So this work is a collaboration project between our university, Antonio, CERN, and SINTEF. So here is the outline. I'm going to talk about the goals of this work and about the material characterization of a specific graphitic material, also proposing some modeling, and finally the conclusions. So let's get started from the goals. Probably most of you know already the Hadron Collider that is placed in Geneva, Switzerland. It's basically just a circular pipe, like 70 centimeters in diameter, very long, underground. And inside of it there are two counter-rotating proton beams that are made to be impact. And there is a device at the end of the circular trajectory, which is basically a damper. So the proton beam needs to be dumped at some point, and this device does that. So the goal of the overall collaboration is to provide a reliable prediction of this device efficiency and safety. So what happens when a proton beam impacts a material? It goes through the material. It's not a physical impact. So there is a sudden thermal expansion. The impacted volume wants to expand, but the surrounding is still cold and constrains the material. So what we expect is an axisymmetric stress state. And of course, this is repeated because the beam impacts are repeated along the time. So what we are interested on specifically is this graphitic material, which is called SIGRAPHEX, and it's a commercial name for a type of flexible graphite. The damper that I showed you before is made of several stacks of different graphitic material, and this material in particular is the one that is getting the worst thermal and mechanical conditions. The goal of the work is very basic. It's to find a constitutive model that could describe the response of this material under these conditions. So what is flexible graphite? I don't know if some of you know already, but it's made by rolling compression of these small particles that have some sort of accordion-like shape, or worms. We call them worms. They are crushed together by rolling, and eventually we obtain a material that, in our case, for example, it has 1 gram per cubic centimeter density. It's provided in sheets of 3 millimeters thickness, and it's basically pure carbon, more than 99% carbon content on it. Its mechanical properties are not really well known, also because the applications are not. Our application is quite unique, I would say. But what we know is that it's orthotropic, so if we pull it or compress it in the in-plane direction, the strength is different, and also if we pull it or compress it in the out-of-plane direction, the strengths are different. About the microstructure, not much we know from literature. This is the density that we are interested on, and we cannot really extract any quantitative measurement, physical quantities from images like this. So it's very difficult to understand how this material is really made inside. That's why we started our material characterization campaign. We started from the very basic. So we did probably the easiest experimental test that we can do on this material. So we had disc-shaped specimens. We tested them in the out-of-plane direction under static compression loading, and we also tried to stack them in a pile of 6 sheets. And this is the response that we got. It didn't change. There is no difference between the single-layer specimens or stack of specimens. So we see an initial. This is the stress-strain curve. We see an initial linear region, a transition, and then the concavity turns upward, which probably corresponds to the densification of the material. An interesting part of this curve is this initial linear region, because we thought that it was a problem for the machine or the setup, but we also found a publication that was describing, that was giving the same results, the same that was showing the same curves, and also at higher density this is even more visible. So this initial nonlinear region appears as a material response. Moreover, we also performed cyclic uniaxial compression, which is basically just loading and loading, loading and loading. And we noticed, as is also quite common in graphitic material, that there was no clear yielding point. There was, regardless of the preload, there was always an unrecovered deformation visible even at very low strains. So, based on these observations, we did a little bit of a review of what are the material models that can kind of reproduce the same behavior and are available in commercial finite element softwares. In this case, the software use this LS Dynamic. And we found that this material is kind of similar to some kind of foams, crushable foams, and compressed powders. These are good candidates for our modeling, but they are not, for example, able to reproduce that initial nonlinear region that we saw before, and also they need to be calibrated usually with multi-axial tests, which is quite complex to perform in this material. So to understand a bit more in depth how this material is made, we used it is made in about the microstructure, which can also give us some hints on how it is made and why it is behaving like this. We did SEM imaging. So basically, we drilled a hole on the top surface of the material. And we cut a section which was perpendicular to the plane of the sheet. The section was big, roughly around 150 microns times 100 microns in depth. And finally, we got the first picture, the first an accurate description of how the material finally is made. So this picture has a lot more information than this picture that we had before. So finally we know how this material is made. And if we go close, then we see that it's a bit messy. So there are a lot of pores, different sizes and different shapes. And we can also see, for example, that there are these layers whose thickness is on the averagely is almost the same, I would say. And these microsheets are also creating the pore walls, let's say, and they are the skeleton of the material. These layers are pure carbon. They are like we think that this is pure carbon, and we call them microsheets because they are stacked of more than hundreds of graphene planes, basically. Moreover, these microsheets in some regions are very well aligned, and they have thin pores between each other. And in other regions they are disordered. They are put in a random manner, and the pores that they create are bigger and more apiaxial. So also to get some quantitative information out of these pictures, we did some segmentation of these images. This was done in MATLAB, so here you can see the area distribution of the pores. You can see that there is a large variation in area, so very small pores, very large pores. We can calculate the aspect ratio, which is lower than 0.5 on average, I would say, and the orientation of the pores, which is like Gaussianly distributed along the horizontal axis, which is expected. So on the base, so finally we have a description of this material, of the microstructure, also quantitative description. Based on this observation, we proposed a simple modeling of this material. So first of all, we assume that the well-aligned regions are more solid and stiffer, and that the disordered regions are softer and behave like foams. That means that they at the beginning are very soft, then they densify, and then they reach a densified status. This behavior can be described analytically by a sigmoid function with some parameters, 3 parameters. Moreover, if we think at the production process, at the beginning we have a bunch of powder which is very loose, so the porosity is very low and the material is very disordered. So during the manufacturing compression, the microsheets start to align more and more, and even more during the compression test. That means that the volume fraction of the aligned region increases all over the compression, and we can describe it in a way with the general expression, exponential expression, and putting all together with a simple rule mixer, we can fit the stress-strain curves that of the experimental stress-strain curve. So we chose only 4 out of the 23 tests that we did, because these were the tests that reached the highest stress levels, and they had the biggest amount of information. And the fitting is quite good, I would say. And what is interesting is that this analytical expression can kind of catch at least this initial nonlinear behavior, which was weird at the beginning. So we have now a sort of mathematical description that on one side can be useful when it comes to write, for example, a user-defined material for finite element software. And also may support the idea that the mechanical response of the material is a contribution of the aligned and disordered regions. The ongoing work right now is that, of course, we did some, I would say, rough field SEM investigation. We can improve it. We can, for example, infiltrate the pores with a resin so that we get a more accurate distinction on the pore edges. This would help a lot for the segmentation algorithm, which still, again, can be improved a lot, because the best thing would be to have an accurate description of the geometry that can be directly exported on the finite elements on the finite element software, so that we have a representative volume element that can be tested. Here you can see a first attempt showing the foamis stress. I reused just simple polycrystalline graphite material properties in this case, but it is something that is still on work. So with this, I'm getting to the conclusions. So finally we can say that we know how this material is made also inside, and we know how to characterize it, at least how to look at the microstructure that is made with, and it is made with 2 types of regions, and they probably play the key role in the mechanical response. The overall mechanical response itself is probably similar to a crushable foam or a compressed powder, at least under these conditions that we saw here. So static uniaxial compression out of plane. But probably we need to get a more refined description of the response, a micromechanical approach, also based on this kind of imaging technique. With this, I conclude my presentation, and thanks for your attention.
Thank you, Emmanuel, for your presentation. Nice presentation. Any question? Okay, we pass to the last. Yes. Thank you very much.